Okay. So as you remember from the last class, we just stopped after discussing a vector space model briefly. So essentially, the vector space model uh, also is similar to the term document matrix. It's actually a term document matrix. It's except that now here the documents are considered as vectors in the term space. Like every term is one dimension, and every document is a vector. So similarly, the query also is considered as a vector in the same space, and then uh, the similarity between uh, the query and the documents based on which the documents will have to be ranked. We discussed that, well, dot product is not such a good idea. So typically the cosine similarity is the angle between cosine of the angle between the vectors. So that's actually one the most common similarity measure that people go with. Okay. So having done this, what we have seen before is we have seen that we have an index, right? So we have an inverted index. So this is also can be converted into an inverted index. This term Diwali, the document D1 with score 0.5, document D2 is not there. The score 0 means not there. So for this term India, document D1 with score 0.2, D4 with score 0.2, D5 with score 0.4, and all that. So basically for every term, we have a list of document IDs and their TF-IDF scores. So the TF-IDF score corresponding to that term and that document, right? So that would be the corresponding inverted index. And in the query processing portion, then what will happen is, of course, query processing can, the goal of query processing can be different. It can also be that return me a full list of ranked documents, or in most practical cases, when you actually want a user to use a search engine, then the idea is you want to return top k documents where k is typically 10 or 20 or something like that. And there, what we can do, so how do you compute cosine similarity, right? So if we just do merge union as we have seen before, right, intersection or union for Boolean retrieval, here what we have to do, we have to compute, given the query, we have to compute the cosine similarity of every document with the query. And if you just look at this portion here, what this means is this is the query vector. We have a 1 here and a 1 here, and these are the document vectors. Now, what would be the cosine similarity between Q and D4, for example? So that would be the dot product by the norm, which means you have to multiply 1 with 0.2, and that's it. Here, nothing else comes. So the query terms are India and statistical. D4 will only appear in case of in the list of India, and the score is 0.2. If you take the query terms as unweighted, that means all the terms have the same weight, then Q transpose D essentially the numerator essentially for every document is essentially just the score it has, right, for these. So for these lists, so for the list India, document D4 has score 0.2. For list statistical, document D4 has nothing. So the total score will be 0.2 in the numerator, and you have to divide that by the norm of the query by and the norm of the document. The norm of the query is constant because we are actually, for the same query, we are ranking all the documents, right? So the norm of the query is also constant. So only variable thing we have extra is the norm of the document. So instead of storing just the TF-IDF scores, if we also store the norm of the document, we can actually compute it on the fly. So for example, if you just look at this in the form of a inverted index, then for India, this is the list. For statistical, this is the list. And for this query, you're going to get this document, D1, D2, and D4 and D5, right? So these are the 4 documents that will come in, and the scores will be 0.2, 0.3, 0.2, and this will be 1. And that you have to divide by the norm of every document, right? So that's what you will have. So yeah, so similar to merge union or intersection, you can simply do that, except that the aggregation function, you simply cannot sum the score. You have to sum the score and then divide by norm of the document. But since we are interested in only ranking, no need of normalizing with the query length, right? So Q norm is not required. The, if the query words are unweighted, this becomes very similar to our merge union. Okay. So essentially, you just have to pre-compute the norm of the document and either keep it in the inverted index or divide the TF-IDF score by the norm of the document already, so that you can kind of just sum them. Okay, so and we'll see a little bit later that bothering too much about exact scores and stuff like that is not really what we would be interested in for several reasons. So in many cases, what people can do is they can simply sum the scores, sum the TF-IDF scores and things like that, assuming, so that would work if norm of every document is kind of similar, or you normalize the scores beforehand for large documents, and then the same thing will follow. So essentially the idea is still follows from our TF-IDF kind of scores. Now, what we need to do is we need to find the top k results after computing the union list or intersection list with cosine scores, right? So essentially what you will have is, if you have a three-term query, right? So you will have three lists, you will combine them, and you will have one single list with scores. But as we have seen before, the lists are sorted by document ID, okay, and they are not sorted by score. So what you need is, finally you want to return results with the highest scores. So what we'll do is you will use a partial sort. So the usual sort would take order n log n, but n may be very large, 1 million or even more. There are some words for which there are more than a million documents in the web. So what you would do is you make a max heap. So it's essentially a binary tree in which each node's value is greater than the values of the children, and it takes order n operations to construct, and then you can read top k, each of the top k in order log n steps, right? So for example, if n is 1 million, k equal to 100, or k equal to 10 will be even better, then this is about 10% or even less of the cost of the sorting. So essentially, it is order n to construct and then order k log n. So instead of n log n, what you have is n plus k log n. Okay, so something like this will be a max heap. So after you have merged the lists with the scores, combined scores, you will create this heap, and then you want finally want the top few, top k maybe 10 or 5 or 20 or whatever, and you can just read it like this. Yeah, and that the complexity of that will be order n plus k log n. Now, yeah, so when n is large and you have a very time bound application, I mean, commercially or even for users perspective, it is definitely much better if you take only fraction of a second instead of, I'm sorry, only fraction of a second instead of 1 second or 2 seconds and things like that. Then these kind of optimizations are actually very important. So this part is clear, right? So if you have a, essentially if you have a list of scores, list of numbers, unsorted, you only want the top k, then you can actually use the partial sort. Okay, so so then overall, what we have learned from the high level picture of search is, we compute term document scores, TF-IDF for similar scoring. There are more advanced approaches. Uh, Now, this may already apply some normalization to eliminate bias on long documents and stuff like that, right? And then if you want, if that normalization was not done before, or you want to do a normalization while computing the cosine, then what you do is you rank by cosine similarity, and it's equivalent to further normalizing the term document scores by document length, right? So the query length normalization is redundant in this case. And then finally, what you do, you compute the cosine similarity, sum the scores with union or sum the scores with intersection, etc. So these are more practical approaches. Inside, instead of cosine similarity, you can simply sum, and it will be much faster to compute. So in a nutshell, you have an inverted index, your query comes, a list of terms, you fetch their posting lists, and then merge the posting lists and rank by partial sort, and that's the total query processing step. Now, one thing I have taken for granted here, that is, your query terms come, you fetch the posting list. So how do you fetch the posting list quickly? We'll come to that maybe later today. At the end, probably I have kept those slides. All right. So now what we have done here is we said, if we have, let's say, three terms in your query, and we fetch the posting lists and then we merge them. And how does that merge work? That merge works something like this. So suppose you have these three posting lists, right? And we said we keep one pointer at the beginning of each list and then move on the list where the document ID is smaller and so on, right? So that we did for Boolean retrieval. There just we are just outputting document IDs. Here we have to also sum the scores or merge the scores or somehow do that. But I mean, the flow is still the same. So essentially it works in the following way. So you kind of swipe through the list and you create some kind of an intersection or union maybe. Actually, for cosine similarity calculation, it relates more to union rather. But here the problem is, if the lists are large, then you will end up scanning the lists fully, right? So if the lists are large, means each of them are like order n, let's say, or the maximum is like order n, then you have to scan the lists fully to compute the intersection. So let's say the lists are large, like they're millions in size, and then also you have to scan the list fully. So every time a query is fired, the search engine will have to actually perform this full operation. Now, one interesting point is most real life queries are AND queries. That means I search with three terms. Essentially, the concept that I want to convey or I want to retrieve um, will only be fulfilled if all the terms are present. So OR is not really a good idea in most cases, most real life queries. Users mean and implicitly. We don't write the and, although you must have seen or you may have seen, you can actually play around with Google's query format a bit. You can write and or and stuff like that. I mean, at least a couple of years ago, those things were there. Google doesn't advertise that because they don't want you to play around. Okay. But I mean, the engine actually has those things. If you ever build a search engine on your own, maybe using Lucene or stuff like that, there are actually query formats in which you can specify. The users can specify whether and or complicated, more complicated query formats. But in real life, we don't do that, right? We just simply write whatever comes to our mind, kind of a thing, in natural language, and we mean this and query thing is implicitly. So this means that most often we are interested in intersecting the posting lists, as we have seen here, right? So the posting lists may be large, but the intersection might be much smaller, and we are interested in the intersection. Now, there are algorithms to find the exact top k. So what you have items or document IDs and scores. Okay, in multiple lists you have to aggregate the lists, aggregate the scores across the lists, right? So some same document ID may be present with different scores in different lists, right? For some term the TF-IDF score could be something, for some other term the same document, the TF-IDF score could be something else. What you want is you want to aggregate and merge. Now, there are algorithms to find the exact top k without going through the lists fully. Uh, Typically, they order the lists differently. Instead of having them ordered by document ID, they have some kind of an ordering with higher scores first, so that they can pick the top without going through the full lists. However, I mean, that's actually also a somewhat involved topic. We'll not go into that. But the main point is, does the exact top k matter? So when we want to return the user the top 10 documents, and we have modeled the document query relationship, document term relationships using some TF-IDF intuitive concept. And then finally, we compute a cosine similarity, or simply summation of the scores across terms for each document and so on. And then we say, okay, this is my best document for your query. This is the second best. Now, for that, does the exact top K in the exact ordering matter? So how much are we sure that the 101st ranked document is less important than the 100th ranked document, right? I mean, what we have done essentially is all the scores we have been dealing with are very simplified models for what information may be associated with the documents, right? We have just kind of counted the number of occurrences or something similar, maybe a little bit of semantics, and there are, I mean, lots of more involved topics in there, but ultimately they don't we haven't really done things deep enough so that we can say, well, if I say one document comes ahead in my ranking, then that has to be a better document, right? So basically that's not really the point. The point is it suffices to retrieve top k documents, with many of them should be from the exact top k, or the others should have score close to the top k. That means, they should all be good documents. We are more interested in the precision than the recall kind of a thing. uh, we want to, if Google returns you top few documents, what you will be happy, I mean, it's okay if there was some other document with that same information slightly better, but maybe you are just happy with whatever you got. That's good enough, right? So something like that. So for that, there are a lot of inexact top k retrieval heuristics. They're all heuristics. So how are heuristics applied, and how are they validated? Everything is numerical. So people figure out that if I use this trick, then this computation can be done much faster, maybe orders of magnitude faster, and I still get almost, I mean, the results are almost as good as the exact ones. So then why not do that? Because we can get a pretty quick result that way, right? So one of the ideas is champion lists. So the champion list idea is, for every term T, you pre-compute R documents of highest score in T's posting list. So instead of keeping the documents ordered by document ID, you first pre-compute the top documents for every term. And this R, now, if the search engine is regularly returning top K documents, that means let's say top 10 documents, and the size of the posting list may be in millions, then R should be somewhere in the middle, maybe 500 or maybe 1,000. So this we call the champion list. Now, R has to be chosen at the time of building the index because it has to be a separate kind of list, right? So it's possible that when the user finally fires the query, user may set the preferences that, okay, no, 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 don't give me top 10 documents, give me top 2,000 documents. I mean, it's okay if it takes time. So then it can happen that R is 500 in the index, right? So the champion lists are of size 500. So then obviously you have to fall back to the older, or fall back to the basic full lists and so on. But in most cases, you will actually need to return top k, which is much smaller than R. So what the engine can do at query time, you, instead of looking at full lists or original lists, you only look at the champion lists. Now what that would mean is, suppose there is a term called information, a query called information retrieval, then there is a small list of documents with high score for information and small list of documents with high score for retrieval. And the hope is, merging those two, or intersecting those two, we will get some documents, and at least k good documents with high score for both. And then they are definitely very good documents to return as the top ranked one. Of course, if you don't get k documents in the intersection of the champion lists, then you have to fall back to the standard way of going through the full lists. So this is pretty much just a heuristic, but for most common queries, this works pretty well. And it works way faster because R is much, much smaller than N. So it works way faster than actually going through the full lists. But anyway, it's a simple heuristic. So another approach is static quality scores. We actually have seen static quality scores before. Okay. So the point is we want the top ranking documents to be both relevant. That means the terms should have high TF-IDF score. I mean, that's how we model. We hope to model relevance. And we also want them to be authoritative or trustable. So relevance is being modeled by cosine scores, or I mean, basically cosine score with the query. So term or square score matching. Authority is typically a query independent property of a document. Is this document a good document? Right? So if it's a good document, then I want this in my search results. If there is significant match in terms of relevance also, right? So, so basically there are two factors here. One is the authority or the quality of the document. Another is relevance with respect to my query. So obviously example of authority signals you have seen whenever you search for a general concept, Wikipedia results are returned early because those are set in a way. Wikipedia, I mean, not the small Wikipedia articles, but somewhat mature Wikipedia articles are considered to be authentic because many people have actually read through and made sure that the information is mostly correct. So Wikipedia among websites, in certain newspapers, if they can be considered as authentic. uh, for scholar search kind of things, paper with many citation is considered important. So basically what this means is that when you search with, let's say, 3 4 keywords of scientific terms, maybe there is a paper only cited 10 times which matches these keywords lot more than another paper which is cited 3000 times. But that other paper 3000 times, because it is so valuable, that may come slightly ahead of the other one in ranking. Well, not if the well cited paper totally mismatches. I mean, if there is if both of them matches, then somewhat the keyword match or the cosine scores and etc can be compensated somewhat by an authority signal here. And page rank we have seen, right? So we discussed it briefly when discussing page rank, the motivation of page rank, right? That, well, the idea that if a term is present many times in a document, then it's relevant. That I mean, then if I search with that term, that document is relevant. That was that's the idea of when you assume nobody is playing foul, but people did play foul. So PageRank actually took care of that, right? So so these are static scores. You remember, PageRank is a single score for a document. It doesn't depend on the query. So how do you then use that, right? So we have been talking about TF-IDF kind of scores, and then we have been talking about authority scores like PageRank, and we want to combine them. And we said, okay, we can combine them by some kind of linear combination. But how do we then compute? Now, when we process the query, we have to kind of combine the scores in a way so that we can get the combined score in the ranking. And then we don't want to also go through the whole list because we want to kind of have kind of a heuristic based process which returns the results much faster but does return good results. So how can we do that? So obviously we assign each document a query independent quality score, let's say between 0 1, and maybe also the TF-IDF scores are also between 0 1, assume. Okay, we can normalize them. So denote this score by GD. So GD is only depends on D and doesn't depend on Q. So then a total combination can be simply score for query and document D. Query Q and document D can be the GD plus the similar cosine similarity or something like that. I mean, you can also do alpha plus alpha times this plus beta times this kind of a thing. Okay. Or you can also incorporate other functions of user happiness and stuff like that. You can incorporate personalization in here and so on. Now, the main theme here is how do you process the query? So how do you compute this combined score? One idea is you order all posting lists by the GD score. So we have been assuming so far the posting lists are ordered by document ID, because otherwise we will not have a linear intersection algorithm, right? So we can just simply keep the pointers in the beginning and then move in the smaller, move in the list where the document ID is smaller, right? So that's a linear algorithm, order n. For that, we need the document ID. I mean, we need all the lists to be sorted in the same consistent way. That means the document ID 1 comes before document ID 2 in any of the lists, right? So that's when we can do that. Now, what if you order all postings by the page rank score, let's say? That means for every term in the posting list, the top page rank document will be the first one, the next one will be the next page rank document, and so on. Now, why would this work? This would work because just like document IDs, this is also a consistent ordering, because the top page rank, so you can basically rename the documents or give the documents a new ID. So consider the whole corpus, whole collection. The document with the highest page rank, you call it document 1, right? Document with the second highest, you call it document 2. So if you order all posting lists by the page rank or this GD ordering or whatever the score, static score, not query independent, not query dependent score, then you can also do the merge just like before, because this is a common ordering for all postings. So that we can actually concurrently traverse query terms, posting lists for posting intersection, cosine score computation, and anything. Now, why is it better than document ID sorted ordering? Because here it not only gives you, I mean, retains your power to do a linear intersection or linear union, it also ensures that your top scoring, I mean, you have top GD scoring documents first. So as soon as you get some significant term matching, that means cosine score or TF-IDF score uh, there, you actually get very top scoring documents. So in time bound applications, so basically what happens is, say, I mean, if we have to return whatever search results we can do in 50 milliseconds, this allows us to stop posting traversal early. That means you you have your full posting lists, not like champion lists, but you have your full posting list, but ordered differently with high scored, high page rank documents first. Then you go through them and up to a certain extent, and then you simply stop. Okay, and because your scores are already boosted by the page rank authority scores and stuff like that, by then whatever you get in the intersection, they are likely to be uh, rather good results. So this is one method by one method to compute top k when you combine authority score and normal term document specific scores. So then there are actually a couple of more ideas there. I'll in this course, to keep things brief and just to give you the idea, I'll skip some of those. But there are also high and low lists. So for each term, what we can do is we can maintain, just like champion list and the original list, we can maintain high and low, like 2 tiers or 3 tiers and stuff like that. So the high can be the champion and low can be the rest. So you first only look at the high list. High list means high scores list, and if we get more than k docs, then done. If we don't get, then we go to the low list. These are all just to make sure that you kind of be lazy, or rather you want to be done doing less work, and then don't read through the list if necessary, unless necessary, and stuff like that. Now, this high list can be made by using either simple cosine scores without the global quality, or you can actually merge them together as well. Now, this also gives you a means for segmenting index into tiers, right? So tiered index like break posting lists into a hierarchy of lists, most important, then dot 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 least important kind of thing. You can do that by different kind of measures. Okay. So then the inverted index is broken up into tiers of decreasing importance, and then at query time, you use the top tier. If it fails to give you k documents, good ones you drop to lower tires and so on. So something like this it can look like. So tire 1, let's say auto is a term, it has doc 2. I mean, here for the example there are only one or two in the list, but in reality there will be more. Okay. um, and yeah, so car has this. So doc 1 appears for auto in tire 3 and so on. Obviously, I mean, this is a very toyish size. In reality, you can assume there will be a few thousands in the tire 1 and maybe tens of thousands in the tire 2 and maybe, hundreds of thousands in the tire 3 and so on. Because, I mean, when you fail to get results within a few thousand, then you go to tens of thousands and then you go to hundreds of thousands. Stuff like that. Okay, at this point, any question? I believe these
Huh?
things have been, yes.
Here, dock 2 in tier 3 and like dock 2 in tier 1 are different docks or same?
Different. Doc 2 in, no, the docs are the same, but they appear for different terms.
If they are same, I mean the tire are,
Hmm?
but tire is the breaking into tire is dependent on some property which is independent of the terms, right?
No, so that depends. Breaking off can be independent or can be you can actually. I mean, you can also do it by some cosine similarity and stuff like that.
Okay.
So
If it was independent, then like one document
then this
would,
should not happen. Yeah.
yes, okay.
So then, okay, just a moment. Then what would not happen is the following. Then for car, doc 1 comes first and doc 2 comes later. And for auto, doc 2 comes first and doc 1 comes later will not happen. Right? So that would be more like just a
Okay.
simple GD
Yes.
ordering. Whereas the picture, I mean, actually, this is taken from Raghavan's book. This particular picture uh, kind of shows tiring of index based on more term document scores. In term specific scores, more of that
Okay.
instead of probably. But you can combine. I mean, for example, for every score, you can also add a portion of the every TF-I DF score, plus you can add a portion of PageRank score. Right. So you can actually,
Okay,
it's
sir.
pre-processing. You can actually do that, and still it can result in such a thing. It's just to show you some picture. It's not really. I mean, yeah, it doesn't have to. You don't really have to read much into this. It's more like you have some tire, you first use this as your index, and if you don't get enough documents, then you use this as your index and so on. All right. So now, so then another cool idea is skip lists. So again, this is it is assumed that you are only looking at intersection of lists. For union, this thing will not work. So look, skip lists are so the look that the posting lists. Let's say here we have document IDs. Okay, we also have the score and more other things in line here, but that's not what we are looking at right now. So suppose we only have document IDs, but in reality we also have the scores. But here it's about merging based on some document ID. If we have ordered by GD ordering, then suppose we have renamed the document by IDs, rename the documents IDs and somehow. So just, I mean, ignore all those things right now. You can actually combine the approaches. So suppose these are the document IDs and you do linear intersection in the following way. So start from the beginning, you determine the smaller ID, move on that list. If IDs match on both lists, you add to the result list, right? So what you do is 2 is smaller, so move here. So next step, what happens? 3 is smaller, so you move here. 7 is smaller, so you move here. Still 54 is smaller, you still move here. Again, you move into this list and so on, right? So what happens is you essentially have to move into one list for much longer. That can happen. And especially that can happen when one of the terms is a bit more frequent than the other. The less frequent term will have bigger gaps in the document IDs typically, and more frequent terms will have smaller gaps. So in your intersection, what might happen is you move 20 times in one list and on an average then once in the second list, or if you have multiple lists that way. So the idea is, can we actually, instead of comparing is 7 smaller than 453? Is 54 smaller than 453? Can we actually jump? So the idea is the following. You keep uh, skip pointers in some intervals. Okay. So how do you use that? So start from the beginning, determine the smaller ID. In this case, 2 is less than 3. So you have to, oh, sorry, you have to move here. Now, is the ID following the skip pointer on the list 2 also smaller than 3? So essentially, what you do, we have reached 453. If this is also smaller than 3, no. Oh, I'm sorry. Uh, no, I'm sorry. Just let's redo this. So in normally what you would do, we would just move here, right, to 453. But now what we'll check, should we move one step or should we move jump to here? Yes, uh, 2 is smaller than 3, but is this also smaller than 3? Then we can actually safely jump here because everything else before will also be smaller than 3. Well, no, in this case, this is not smaller than 3. So we have to be conservative and we have to just move on. Now look at this. 3 is smaller than 453. So we know that we have to move in this list. But should we move one step or should we jump? We can check, we jump, we follow this pointer and check that, oh, 322 is also smaller than 453. So we can actually jump straight here. So what we do is we can actually save the comparisons, these comparisons, right? So we save these comparisons, directly jump here. Then we compare this with this and so on, right? So essentially, um, what we do is that we hope that in sometimes during the query processing or intersection, we will be able to jump instead of going one step at a time. So in that hope, what we do is we build the index with extra pointers, extra skip pointers. But where do we place the skip pointers? This was just an example to show you, right? Do we place it every 4 elements or do we place it every 1,000 elements? What do we do? So the trade-off is if we have more skip pointers, then we have more comparison overhead. That means suppose you have a list of 1,000. I mean, I'm just discussing in small numbers. In reality, these will be useful when you have millions. So suppose you have a posting list of size 1,000. If you put skip pointers every 10 elements, then you have 100 skip pointers. Well, then this means that uh, every time, I mean, so many times you have to check, should I move, should I jump, or should I just move one pointer? If you don't have so many skip pointers, then you anyway, you are less likely to be so lucky. So being able to skip using the skip pointer is just getting lucky, right? I mean, you can actually jump and you don't have to compare with all the numbers before that. But if you put too many of them, then like you have to compare too many times. If you put too less, then you are not lucky enough. So again, this there cannot be any theoretical results on this because it all depends on how the data has panned out. So the empirical trade-off, people figured that for a list of size n, you can keep root n evenly spaced skip pointers. That means you keep root n skip pointers of every skip pointer will have, skip root n steps. Of course, I mean, if there is, if n is not a perfect square, then you just approximate somewhere. So that's just an empirical trade-off. The problems, however, are building at indexing time is easy. I mean, you simply build a posting list, write it up in the file and so on, and you can put the pointers. But maintaining is difficult if the index is updated frequently. That means if new documents are added or deleted every now and then what happens is, uh, so suppose some in the posting list some document was there, it has to be deleted, or some new document has to be added, then things have to be inserted. Then your pointers get messed up. So in particularly, you have to be careful with deletion because it may happen that the pointer the skip pointer is pointing to a doc ID which gets deleted. So that's pretty much the point. Okay. So yeah, I think I will just quickly discuss pre-processing of a document for a moment, for 2-3 minutes, and then we'll move to the discussion of the quiz. So we have essentially covered a very basic introduction of search engines. In reality, of course, what happens, documents come in the form of text, word or xml or html and stuff like that. uh, there is a lot of pre-processing before you get to the inverted index at all. So decoding of this format, and then they're converted into simple text, ASCII or Unicode or whatever it is. Then they are tokenized. So tokenized means, typically, now this will not go into the details of tokenization. Tokenization can happen in many ways, whether you should simply split them by space or space and punctuations or some other way. Essentially, tokenization will give you sequence of tokens, which typically you might use as terms, and then maybe some more linguistics processing, and then you will get your dictionary, the list of terms that the search engine knows. And of course, and consequently will also build the inverted index. So in that, this processing, there are some important steps that are followed typically. One is removal of stop words. So it's words like of, the, and very frequent words which appear everywhere, but they do not really bear any concept. So you can actually remove them because they add noise to your vector space model. They are not useful, but they increase the dimensionality unnecessarily. However, modern search engines, they do not completely remove stop words, because things are going from just a collection of words in a document to more well understood natural languages, right? So we are so things have advanced a bit. So modern search engines don't completely remove stop words, and also whether you use of or the, that actually changes the meaning, right? um, then another is stemming. So stem means root. So every word has some root. So for example, statistics, statistically, statistical, they all go to statistic. So you may want that when the user is searching for statistics, uh, statistical documents with statistical are also found, because it's pretty much the same concept. Now, this means if you convert all words to the root of the word and then think that they're all the same, then you lose slight information. The form of the word matters sometimes, but unifies differently expressed queries on the same topic. So if you do that, then Indian Statistical Institute and India Statistics Institute will mean the same. Lemmatization is the stemming is actually a rule based, typically a rule based method, and lemmatization is more like morphological route. So using stemming, if you convert saw, it should have been c. C is the root of saw, but saw will go to s. Okay, and there are many others like that. Then normalization, unify equivalent words, or uh, um, 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 acronyms and stuff like that as much as possible. USA, United States of America, they all mean the same. Okay. Windows, capital, small, do they mean the same? You have to figure out and then unify them and so on. So we'll not cover the details here, but the idea is that you you pre-process the documents, all of them, and then go to building the term document matrix or the inverted index or whatever it is. The dictionary um, typically works in the following way. User sends the query. The engine has to determine the query terms. So basically query is parsed, right? So if it's 3 or 4 words, then just detect the words. That is easy. Or I mean, even there are advanced works on that also, but the simplest form of that is easy. Then the second thing to do is determine if the query terms are present in the dictionary, right? So for that, there needs to be a dictionary lookup, and a lookup can be done using either a search tree or hashing. So something like this: user gives a query, the search engine has a dictionary, and the dictionary has posting lists. For every term has posting list pointers to posting lists. So what the this portion needs to do is given the query, it needs to figure out, okay, where are my posting lists, or do I have these lists at all, right? Maybe this word is not present. I don't know the word, so that can also happen. So to do that, binary search trees are some form of binary search trees are actually binary or B plus tree. We'll see in a moment. So binary search trees are good options. Each node has two children, right? Order log m comparisons if the tree is balanced. The problem here is balancing the tree when the terms are inserted or deleted. So binary search trees are good for this because if you have to figure out whether some particular term is present, you can actually use log m lookups and come here. And maybe here, if the term is present, then there is a pointer to the posting list. However, maintaining it will be a problem. So that's why people use B tree or B plus tree. So B trees are uh, just an extension, but they're not binary anymore. So number of children for each node is between A and B for some predetermined A and B. So there's a flexibility in there. Okay. So which means you have a root here, maybe you have some middle level things here, and then mm, again you need order log m comparisons, but order log m to the base a, which means typically it's much less than the binary search tree, because what you are doing is you are flattening this a bit than the binary search tree. So maybe after the root you have 100 such things, and again for each of them you have a few and so on. And what can happen is often this top level thing, often for search engine, you can actually get away with just a two level B tree or B plus tree. Uh, so a B plus tree is similar to B tree, but all the data pointers to posting lists are in the leaf nodes. So, so what can happen is you have a root, then you have ranges like 0 to 7, X to Z, A to C, or whatever. You have ranges, and they point to again each term a level below. And this whole dictionary may be very big, and you may not want to keep it in the main memory, but the top level may be not so big, and you can keep the top level in the main memory, and the bottom level, whenever query comes, you can actually look up in the top level, but that can be done in memory, so it's quick. And then it tells you, okay, these are the places to look for in the bottom level, so then you can quickly fetch portion of the bottom level and do a lookup and find the term. And then when you do that, there will be a pointer to the posting list like this. So essentially, let me go back in this picture once. Yeah, so here this dictionary is essentially, let's say, a B plus tree, where you have a root, you have a top level, and you have a bottom level. Okay, so a final goal is tell me where my posting lists are, and then the search engine will actually start from the posting lists and read them or fetch them and or do whatever it will do. Okay, so final thing that I wanted to mention. So the simple things that we have done so far cannot answer phrase queries, right? So phrase queries means I want these three terms to appear just one after another. I don't want that a document has Indian somewhere, statistical somewhere else, and institute somewhere else. So for that, what people do is they use positional index. Together with the term document IDs and score, store the positions where the term occurs in each document. Okay, so something like this. So let's say this term occurs in document 3 in position 1. And also something that I have not written here, also the TF-IDF score of Diwali and D3 here. So basically the document ID, the score, maybe the GD score, maybe the per term TF-IDF score, whatever. There may be more things depending on how complex your query processing is, and the position. What about this? It means it appears in D2 in two positions. Okay, I mean, typically this will not happen that in one same word is present in fourth and eighth position. This means this is the fourth word in the document as well as eighth, but it's just an example. So typically in long documents, some term may be present many times, so you will actually have the positions also listed. So this is the positional index. Again, I repeat, not drawn on the picture, but the scores, TF-IDF scores, can also be embedded in here. So this pretty much looks like a full search engine index, a basic but fully functional search engine index, which can support phrase queries. How? You do the same kind of intersection, but if the query is India Statistical Institute, you have to match not only the documents where all the terms are present, but you also have to make sure that they are present in the order they are wanted. So 8th position, 9th position, and 10th position. Okay, so I mean, just in this example, I have shown that that happens, but there may be many documents in which the positions are not matching, so it will not come in into our search results. Okay, so there are other approaches for phrase queries, some approximate approaches, and so on. So which I will not cover in this course, but that pretty much covers the overview of what I wanted to do on search engines. So just a picture, documents, you parse and do linguistic, I mean NLP operations and stuff like that. There are some things which we did not discuss, and let's forget this. Then indexing. Okay, so yeah, so there may be this inexact, high list, champion list, and so on. There may be tired index. There may be other kind of indices which we have not covered here. So basically all kinds of indices here. The user, so this is the pre-processing stuff, pre-processing done. The user fires a query. You figure out what the query means or what the different terms of the query are. You may want to do a spell correction. Again, we have not covered that. Then you search in the indices. The engine does the query processing, returns score and ranking. Then, after the initial level, there may be a machine learning based ranking further. Okay, so there may be a training set which so given previous queries and user actions and stuff like that, which ranking is better and so on. So there may be other parameters which you combine, and finally all of this happens and goes to result page. Of course, as I mentioned you before, the modern search engines have progressed a lot. There is question answering and other stuff which are uh, the trend is like that. So we will not cover those in this course. Probably it's in the scope of an NLP or IR course later on. All right. Any question as of now? Anyone? Okay. All right. So I think then I'll just stop the recording.